partial z, partial x1 generally will be negative. So that's why we're allowing partial z, partial x1 to be less than or equal to 0. Plus, the next part is this. Oops. Let's just leave a space, not a plus. The next part is we'll just restate this non-negativity condition. x1, of course, must be greater than or equal to 0. And the final part is this. x1 times partial z, partial x1 must be 0. This is sometimes called the complementary slackness condition. In other words, suppose partial z, partial x1 is negative. Now, what that would mean is really what you want to do is decrease x1. But you can't because it's at 0. So if partial z, partial x1 is negative, then it must be the case for this condition to hold that x1 is 0. Okay. Let me explain it more simply, these non-negativity conditions. Suppose you didn't have any constraints at all. And suppose your objective function, here's x1, here's f of x1. Just one variable, x1. Suppose our objective function looks like this. What would the optimal value of x1 be? Just looking at this, what would the maximum, if you wanted to maximize f, what would you choose for x1? 0. Because even at 0, this thing looks like it has a negative slope. So you would like to make x1 negative, but you can't. So now, what is the condition? The condition is x1 times f prime of x1 equals 0. So if f prime is negative, then you would set x1 equal to 0. Okay. For x1 positive, then you would want f prime of x1 to be 0, as we had before. Okay. This would be your typical interior solution. Okay. But if you have a non-negativity condition, then you would have this. Okay. Oh, you could collapse this statement into this. F prime of x1 is less than or equal to 0. x1 is greater than 0. And complementary slackness is this. See, this is the format we're using. And this is why this condition arises here. Now, you would have the same thing for variable 2 and for all the way down to variable n. So these would just continue down. Partial z, partial xn must be less than or equal to 0. X sub n must be greater than or equal to 0. And complementary slackness would require that xn times partial z, partial xn equals 0. So this is the first part of the Kuhn-Tucker conditions for x1, x2, xn. But then you've also got your Lagrange multipliers. So on this side, we're going to have this partial z, partial lambda 1. We're going to require that that be, notice partial z, partial lambda 1 is just this. Now we're going to require that this be greater than or equal to 0. Because this term here could be less than R1. For example, our expenditure on the goods, the end goods, could be less than our income. So we're going to allow this. Partial z, partial lambda 1 must be greater than or equal to 0. We're going to require lambda 1 to be greater than or equal to 0. Lambda 1 is just the Lagrange multiplier. Remember, the Lagrange multiplier tells you how much the optimal value of your function increases for a 1-unit increase in the constant. So we're going to require lambda 1 always. All the Lagrange multipliers have to be greater than or equal to 0. Okay. And then finally, the last term is complementary slackness again. Lambda 1 times partial z partial lambda 1 equals 0. In other words, that means if partial z, for example, partial z partial lambda 1 is positive, so that this term is greater than this, so that you're not using all this constraint, then that's going to mean, for example, if this is positive here, that means lambda 1 is going to be 0, which makes sense. Because if you're not using all of this first constraint, if you're not using all this first constraint to get more of it, it's not going to help you. Then the Lagrange multiplier would be 0. Because you're not using all this anyway. Okay. Then these same sort of conditions hold for all the Lagrange multipliers. So this would go down to the last one, partial z, partial lambda sub m. That has to be greater than or equal to 0. Lambda sub m greater than or equal to 0. And then complementary slackness. Okay. Okay, I know this may seem rather abstract. This is these conditions are going to be the same for a maximum or a minimum. The only difference is your constraints are greater than or equal to rather than less than or equal to for a minimum. That's the only difference. But these conditions are the same. Let's take a simple example to illustrate this. A very simple example. What's fun, these problems sometimes are called, where you use the Kuhn-Tucker conditions, called nonlinear programming problems. What's fun about these problems is you get to guess at what the right solution is. You can't know in advance which guesses will be right or not. So sometimes you make wrong guesses. That makes it more fun than normal. Let me take a very easy case. Suppose you want to maximize utility. As a function of how much of those two products you consume. Let's take a very simple utility function, x times y. It's about the simplest one you can think of, really. It makes the math easier. And you want to maximize that utility subject to these constraints. One constraint, let the price of x, the price of y both be 1. Let income be 100. So one of the constraints will be x plus y is less than or equal to 100. Let me write this down. We're assuming px equals py equals 1. We're assuming I, income, is 100. Okay, so that's one constraint. And I'm going to write it in the proper way, less than or equal. Then there's another constraint. Let's assume that there is wartime rationing, and as a result of this, consumption of good X, which is maybe used in the defense of our country, is subject to a ration. So X is less than or equal to 40.